Hi, welcome back. In the previous video we looked at how the basic operation of an op-amp works. And in summary, if you think of an op-amp as having an infinite gain and that the inputs have a very high input impedance so they don't consume any current from the supplying circuitry, and that the op-amp will do whatever it can to get the positive and negative inputs the same. So if the positive input is higher than the negative, its output will go as high as it can up to the supply rail or very close to it in order to get the negative input to the same value as the positive. And if the positive goes below the negative, it will pull the output down towards ground in an effort to try and get that negative input back to the same value as the positive input. All right. Now, without going back over what we did before, if we just remember that we have this divider chain, R1 and R2, that tries to provide a higher output range than what our control circuit is here. All right, this is our 0-volt rail, and we've got a 5-volt reference feeding into our potentiometer here. So this input can go from 0 to 5 volts. We need this feedback to go also from 0 to 5 volts. So if we could keep with the theme that our output wants to be 30 volts, then if we have a 50K on our feedback and a 10K at the bottom, that gives us a 6 times gain on 5 volts would give us 30 volts output. Now, as we said before, the output doesn't have much of a current drive capability. So how do we increase this? Well, one of the first obvious ways, all right, this is the basic circuit we had before where it's feeding directly back from the output of the op-amp. So if we break the output of the op-amp, all right, and we put something else in here to increase the drive capability. So one option would be, say, just a simple bipolar transistor. All right. So if we put a transistor in here, let's put a resistor in to limit the current as well, just so we don't overload the output of this. If we put a transistor here, all right, and this goes from, let's just say we've got 30 volts up here, this would now be our output. Now, if this is the output terminal to the load, and this was our 0 volts on the load, all right, if we took this feedback and we connected it to here, then what's going to happen is the transistor is going to be driven by the output of the op-amp, and you're going to get the gain of this transistor into play. So if you're pumping 30 or 50 milliamps into the transistor and it's got a gain of say 100, now you've got so you've got 50 milliamps in, so you've got 10 times the 5, so you've got about 5 amps potentially coming through here if you can put 50 milliamps. If you want to make sure you're not overloading your transistor, then maybe go with 10 milliamps down here. Okay, feeding through this transistor, then if that's got a gain of 100, that would give you 1 amp output basically. All right. Now, a way to make this even more able to drive the output would be maybe to use a Darlington driver. All right. What that's going to do is increase your gain. Now, you can do this with you can do this with 2 separate transistors, or you can do it with let's put a resistor in here to limit this current as well. You can do it with a Darlington driver, which has all of the circuitry built in. Either way, this would allow you to drive that output to quite a high current depending on what you've got. So if you had a 2N3055 or something like that, you could maybe go up to up to 10 amps or something out here. If this circuitry had a gain of maybe 500, 10 milliamps in here is going to give you basically 5 amps on the output. I think 10 milliamps, 100 milliamps, 1 amp times 5, yeah, 5 amps on the output, which is pretty good. But the problem with a transistor like this is you're going to get about 2 volts dropped across this transistor. It's just because of the way it works. You're going to drop about 1 or 2, a couple of volts here and maybe a 1 or 2 volts across here as well. So if this is running on the same voltage, you got 30 volts here, you've got dropped, you know, a couple of volts across the base emitter junction of this transistor and maybe, you know, a volt or two here. That means your output can only maybe go to about 28 volts or maybe even a little bit less, which for most purposes that will probably be okay. And if you increase this supply voltage here to say 35 volts, then, you know, you're still going to be able to get your 30 volts out. So that's one way that you can easily increase the current here. You know, this resistor would be set as a value that would, you know, allow just to limit the current going through here. So maybe it would be, you know, 100 ohms or something like that, just to limit the current. But it's going to basically be an emitter follower is what this is going to work as. So whatever this voltage is doing here, this is basically going to follow it, but with two base emitter junction drop voltages across it, and then the current output is going to be based on whatever the gain of this circuitry is based on the current feeding in. And your load is going to sit across here, okay? So as long as your output is able to drive whatever this load is going to be, so maybe you're driving 5 amps down here, what you're doing is you're actually monitoring the voltage, because your feedback loop is taken from the positive terminal of your output, and there's your negative. So if you want to get, say, 30 volts here, this is, again, remember the op amp's going to drive as high as it can to drive this output to the point so that the feedback is 30 volts, and your 50K 10K is going to divide this by 6, and you're going to get your 0 to 5 volts in that's going to follow your 0 to 5 volts from your voltage reference. All right, so that's a very, very easy way of increasing this. Now, what you have to remember here, though, is heat. Okay, you've reduced the amount of load on your op amp, which is great. It's going to be, you know, running fairly cool and things like that. But if you're dropping 2 volts at 5 amps, that's basically 10 watts that you're dropping across that transistor. Now, that's assuming you've got the full output of 30 volts. Or, you know, if this is 35 and you want 30 volts, then you're dropping 5 volts here at 5 amps. In this case, that we're looking at 5 amps. That's 25 watts that you're dropping of heat that you have to get rid of. That's going to require quite a bit of heat, quite a big heat sink in order to be able to get rid of that that dissipation. Now, that's only when you've got your 30 volts here. If you actually set this to something like, say, I don't know, 5 volts, all right, then what you've got now is, if this is 5 volts that you've set, that means that across here, all right, you've now dropping 30 volts. So 30 volts, if you're still driving your 5 amps, all right, 3 5's 15, that's 150 watts that you're now dissipating on that transistor. That's a huge amount of heat that you have to get rid of, all right? And that would take a considerably large heat sink. I was doing some calculations a little bit earlier. You'd need a heat sink that probably has 0.05 degrees C per watt into ambient 25 degrees C temperature, and that would be assuming that you're not using any insulating mica between the transistor and the heatsink either. So you'd have about 0.5 degrees C per watt between the transistor body and the heatsink, and probably, you know, a similar amount, 0.25, 0.5 watts per degree C between the actual silicon and the case of the transistor as well. Now, I know bipolar transistors are not that good, so if you wanted to have a single transistor here or a Darlington driving this kind of load, you would have to have a very, very big heatsink, or you would have to put a few transistors in parallel in order to, you know, and on separate heat sinks in order to be able to dissipate all that heat. Because that's a big problem when you do something like this. When you're running at the lower voltages, if you've got this high voltage here, you've got to be able to get rid of the heat. Now, one trick that you can actually do, which is one of the ones I'm going to do with my power supply, is when you're running at a low voltage, say like 5 volts on this output, you don't need 35 volts here. Now the transformers that I've got are actually 15 volts times 2 on the transformer. So I've got 0, 15 and a 0, 15 RMS output. So if I put them in series, that gives me 30 volts RMS out, which is more than enough to get me 35 volts up here to do my high voltages. But if I put them in parallel, that gives me 15 volts coming out of it, and I double my current, but I also only halve the voltage. So I basically make a significant reduction in here, because now instead of, if I've got 15 volts up here instead of 35 volts, say 20 volts, because I've 15 volts RMS, so the peak, once you've smoothed it, maybe 20 volts. So I'm actually only going to be dropping 15 volts here at 5 amps. So 5, that's only going to be about 75 watts now dissipated here, which is considerably less than what you would have had if you just had a fixed transformer. So that's something to think about when you're designing your output stage and how much current you want to have. Anyway, going back to the basic drive circuitry here, you've got a Darlington driver pair, and you're able to now drive this right up. Now, one of the issues with this circuit, the way I have it currently drawn, is that this output, in order to get close to the supply rail, assume that this op amp can maybe only go to 2 volts less. So maybe this can only go to, say, 33 volts here. All right, it's dropping a little bit across the resistor. You've got maybe 2 volts. If you're working this heavy, you've got 2 volts and 2 volts here. So 33 less another 4 volts. That only makes it about 29 volts on this output. So as a maximum, that's not very good. So how can you improve this? Well, there are ways you can do it, which is actually very, very simple. And that is to just rearrange how, and it involves one more transistor. And if I just erase this a second, all right, and we'll show a different circuit here. If we actually put this to a small transistor, and this is running to ground, all right, to the 0 volt rail, and this transistor is driving a PNP transistor instead at the top here. So it's very much like a Darlington, except that put a resistor in there to limit the current, maybe 400 ohms or something. This is going to limit the current that's flowing down here, all right, but it's going to turn this transistor on coming from the plus 35 volt rail, and this one is going to drive now the power transistor that's coming from the same rail, and this is going to be your output, all right, and this feedback is still going to come from here, all right, and then you've got your 0 volt output. Now what's happening now is all you've got is this only has to go from 0 to 1 volt or something like that on the output in order to turn this transistor hard on. But you put a resistor in here, of course, to limit the current. You wouldn't want to not have that. So it's a current device. Your output's going to go high enough to be able to start turning this transistor on. As this transistor turns on, it's going to start pulling a current through this emitter base junction down through the 400 ohm resistor or whatever value you have here to limit the current, and it's going to pull it down to ground. Well, this transistor being an NPN, its output, it's not ever going to go above about 0.6 volts from the ground. So it doesn't take much for this op amp to actually drive this thing into saturation. The resistor here, maybe it's 1K or something like that, or maybe a 5K, all right, is going to limit the current. And then if you've got a gain, between these two here, you're still going to get a gain of maybe 100 to 500 or something. So it wouldn't take very much to be able to now have a high current output on here. But this op amp now doesn't have to go to the full rail supply to turn this hard on. So you've now eliminated one drop out of the circuitry, all right? This only has to go a little bit up to be able to turn this on and drive this heavily to get an output. You're still going to have, though, you've got a junction drop here and you've got a junction drop here. So you're still going to lose maybe 4 volts if this thing is drawing a high current. But at least you've now managed to get it up that extra bit so that you can get to your 30 volt supply. And this is still using a standard bipolar transistors. You're just using a PNP, an NPN, and a smaller NPN as a drive circuit to get you from a low side drive up to the high side and allow you to control this output without having to have an op amp that can go to the plus rail. Now, there's still a slight issue with this circuit in that if this op amp is not rail to rail, then if this is basically can't go maybe lower than 0.6 or 0.8 volts, that could be higher than what the junction turn on threshold is for this transistor, in which case this could experience a very small amount of leakage current through here. And if you did get something like that, it's very easy to fix. All you've got to do is basically put a diode in here, increase the voltage threshold. Now you've got 2 diode drops. All right, so you've got maybe 0.6 to 1 volt here, 0.6 to 1 volt there. Now you've got the output has to go at least 2 volts above ground in order to start turning the circuitry on. And you can basically eliminate this 0 volt current, quiescent current that would be flowing and driving this output slightly. So it actually allows you to turn it completely off. And I think that pretty much covers what you would be doing with a bipolar transistors. Again, like I said, you've still got this 4 volt drop on the output. So the next video I'm going to quickly do is how you would use an N-channel FET to drive the output, and also using a P-channel FET. All right. Now the difference is that a P-channel FET is you pull the gate negative with respect to the source in order to turn it on, whereas a N-channel FET you have to take the gate positive with respect to the source to turn it on. All right. But anyway, that's for the next video. So for this one, what we've got here is a very simple way of increasing the output of a power supply from an op amp and still having this feedback through the divider network to give you your 0 to 5 volt for your VREF and providing a 0 to 5 volt back. And what we've done is I've now shown you 2 different circuits. One where you're just using an emitter follower to get your output load up to a very high current, and another one using a low side current draw into a PNP transistor in order to allow your transistor to work, your op amp not to have to go up to the rail in order to drive this. Now, there is a huge benefit to this circuit as well. If you start looking at buying op amps, you'll find that if you're running a power supply at say 35-40 volts for the main rail so that you can get a decent 30 volts or 35 volts output, you start finding it very hard to find op amps at a reasonable price that work up at that voltage level. All right. Now, if you're using this arrangement where you have an NPN transistor driving to 0 volts and actually pulling a PNP transistor down to turn it on, then this output here never has to go much above 4 or 5 volts, allowing for depending on what resistor you put in the base of this transistor here. And because of that, this V plus does not have to be 35 volts. This could simply be maybe 15 volt supply here, all right, to power this op amp. And that's more than enough to be able to turn this transistor on and drive all this. It's all based on the common 0 voltage reference. So now you've got a much simpler and you can, op amp circuit. You can choose a cheaper op amp, and you can even get a lower cost voltage reference design or chip, because you no longer need one that's going to be able to go up to 35-40 volts. You can actually power the voltage reference in the op amp off of say 15 volts, and that gives you a lot more devices to choose from. Anyway, that's the second video done using bipolar transistors. In the next video we're going to look at using MOSFETs, both a N channel and a P channel. I may do it over 2 videos, but either way, that's what we're going to look at next. And that what you're going to find with those ones is it's going to give you even more output capability, and you'll be able to drive those devices much closer to the rails of your supply because of the very low input to output the drain source resistance when those MOSFETs are turned hard on. They go to a very, very low resistance across them so that you have negligible drop when they're running at very high currents. So anyway, you'll see how that works when we get there. All right. Anyway, for now, that's this one done. If you have any questions, please provide feedback. And if you like the video, give me a thumbs up. But anyway, see you in the next one.